Well, now we're going to take a look at the pseudocode required to implement the recursive trapezoidal rule. It's very simple, very few number of lines, but you will have to fill in some of the missing details. Okay, we're going to start off with m equals 0. M is going to be the recursion level. This is just a comment. Recursion or iteration level or iteration number, something like that, starting off at 0. H0, H we're always going to think of as being an interval width. It starts off being the width of the entire interval from A to B. So I'll just say interval width. And then we're going to compute the first estimate of the integral. It is denoted this. It's a sum. S is for sum. Trapezoidal sum. And 0 represents, I could have put an M here. It represents the recursion level. I'll use superscript M inside the for loop. And if you'll notice, this is just the area of a trapezoid. It's 1/2 the width times the difference of the two heights of the endpoints. Basically, if you don't remember, we've got two parallel lines here, and then something like this. What this gives you is almost like it's like length times width, only if you take the midpoint between these two heights, it'd be something like this right here. And that should have been a little bit lower than that. But basically, the area of this trapezoid, if this were correct, if this were more like that, the area of that trapezoid is equal to the area of this rectangle. When you take the midpoint of the heights between these two heights, the height f of A and the height f of B. So that's just the area of one single trapezoid, and that could be considered, I'll just put one trapezoid. That could be considered an estimate of the integral. Typically it's not a very good one, but it could be. It's our initial estimate. So now we're going to do a loop where m is my recursion level, so I'm going to say m equals m plus 1. So now I'm getting into the second recursion level, and second. If I call this the 0th, then this would be the first, because m just went from 0 to 1. And now I'm going to compute this sum, which is really S1, subscript t. So I'm going to use two trapezoids. And the nice thing about this is it's going to start off by just saying, I'm going to use 1/2 of the previous one. Previous sum. Don't put 0 there because it's going to change every time. When you're on the 8th iteration, the 8th one is going to be half of the 7th iteration, plus all of the new data points that have been added. If you think about it, when we have 0, let's say we go from 0, 1, 2, 3, 4. So we have 4 sections. When we double to 8 sections, it's going to go x0 all the way up to x8. That's going to give us 8 intervals. The only new ones being added are the odd indexed ones. The even ones were from the previous iteration here. So here I'm just going to do multiply times the current value of h. I'll explain what that is in a minute. You probably remember. And in this one I'm going to go k equals 1 up to 2, I didn't have to put that in parentheses, but it's 2 to the m minus 1. Because what we're going to add up is f of x sub 2k minus 1. That is essentially, I'm going to put another 2 lines in here, but this is almost the entire pseudocode for the recursive trapezoidal rule. Okay, so let's say that m is equal to 3. I just want to justify this statement for a minute. M equals 3 implies 2 to the 3rd, or 8 trapezoids or intervals. I'll put 8 trapezoids. So what is all this doing? Well, notice we're going from k to 2 to the m minus 1. 2 to the m minus 1 would just be 2 squared. So we're only going from k equal 1 to 4. K equal 1 to 4. And what are we adding up here? If k goes from 1 to 4, we're adding up f of x, 2 times 1. Then when k is a 2, we get x of 3. When k is a, let's see, we're going up to 4. When it's 3, we get x of 5, and then we get x of 7. This is adding up all of the f of x odd terms. The even ones were computed in the previous iteration. That's the entire algorithm. Now we, though, need to figure out, when do I want to bail from that loop? And we'll do as we normally do. We'll compare this value that we just computed with the previous one in computing the relative error. Relative error is a big fraction where we're going to get this term on top minus the previous one minus s m minus 1 t, and then you divide it by, as usual, that. And I'm going to put absolute values around it because the relative error, it's an absolute relative error like that. And then we just put until rel error. Let me see, I think I did the less than 10 to the negative 4. That's good enough for your homework. Now, one more thing you could do is say or m bigger than 100, something like that. There's no way it's going to require 100 iterations. It's going to be less than 10 iterations to get where we need to go, I believe, in our homework problems. But it's nice to have a bailout just to make sure you don't get in an infinite loop or something like this. So that's, you could actually even use a for loop if you wanted to, for I equals 1 to 1,000, but you're going to break out of the loop as soon as this condition is true. I said 1,000 or 100. 100 is plenty. Let's see, just as a reminder, this is we're going from the interval from A to B, right? So we've got a function, A is the left endpoint, B is the right endpoint. So our points in an iteration, I'll just say A is always x0, and then the next one is x1, the next one is x2, and it goes all the way up to xn, which is B. So notice we have actually n plus 1 x values, evenly spaced, n plus 1 because it starts at 0, and that gives us exactly n intervals. The way you will do these loops, like in this, for example, is remember, I'll use a different color, that A is equal to x0, we already know that. X1 is x0 plus whatever our value of h is for the current interval. The h is the width of one section in the divided interval from A to B. So h is initially h0, b minus a. h1 is half of that. h2 is half of that, and so on. So x2 would be x0 plus 2hm, and so on. Goes all the way down to xn, which would be x0 plus n times hm. That's how you can loop through all of the points, or if you need to loop through all of the odd valued points, this will help you get there. And let's see, one more comment. This right here, I didn't define what that is. Well, the first time you come through, h HM is the whole width. That's H0. I want H1 to be half of that. So I could simply do this. Forget the H sub M. Just use H. I'll go ahead and use H0 since I wrote it up here before. Equals 1/2 of H0. And then I could just use H0 right here. I'm not keeping a whole array or a whole list of all of these values, H0, H1, H2. I don't care. I just need to know that each iteration through here, it's getting cut in half. So if you got, in the code, you could call this just H if you wanted to. So H would be 1/2, it becomes, or H is equal to 1/2 of H, and use H right here. H will always be updated because of this. And for the homework problem, just in case it's been a while since you had calculus, this integral is, let's see, sine squared x plus a constant. Simple use of substitution, but if you've forgotten how to do that, you'll need to know this. And that's it.